look at shadow problems and see if there's anything new to learn here. First of all, let's talk about why shadow problems are a thing. It turns out that at any time of the day, the angle of the sun's rays as they shine down on all the objects in one location form proportional right triangles. So if this is a person standing here, and this is a giant tree, their shadows on the ground are proportional at that moment. And we can use proportions to solve for the height of the tree, which is kind of hard to get at, or any other measurement in the picture. Early in the day, the angle of the sun is very low, like these blue triangles. But in the middle of the day, the angle of the sun is very steep. And in fact, there may be a certain time of the day when it's so steep that you don't have a shadow at all. Sometimes in these problems, you'll have your two objects so close together that the small shadow is swallowed up by the bigger shadow. These are still proportional, and you can form right triangles and use proportions to solve for any parts of those. So generally, shadow problems present one of these three situations. Let's look at some examples. Here's a typical example where we're looking for the height of some very hard to measure object. You can't just take a tape measure and find out the height of the Eiffel Tower. But you can measure a person's height and a person's shadow and even the shadow of the Eiffel Tower without too much trouble. So we're going to use those three measurements to indirectly calculate the height of the object that's hard to measure. Now remember, there's 4 different ways to set up any proportion, so we just choose which way appeals to us. I think I'm going to start with the person's height compared with the height of the tower. So if I do that, then I need to put the shadows in the same order. So I'm going to put the person's shadow and the shadow of the tower. If we cross multiply, we can solve this. So 2x is equal to 1,968. We divide by 2 and get 984 feet for the height of the tower. Now in this particular problem, there's also a quicker way to do the problem. If you're paying attention to these measurements, you might have noticed that the person seems to be 3 times taller than their shadow is long right now. That relationship has to be the same for the tower also at this exact moment. So a shortcut would be to just multiply the shadow of the tower by 3 and you still get the exact same answer. Here's a less typical example. We've got a wall that's 30 feet tall and its shadow is currently 40 feet long. And there's a crazy guy standing on top. Okay, they're just having a good time. So anyway, that person is standing on top of the wall. Well, it's pretty hard for me to figure out how tall that person is because they're so far away. And their shadow is right here. It sort of joins at the end of the shadow of the wall. It turns out that their height and their shadow are still proportional because of the angle of the sun at this moment. So we can use proportions to solve for that person's height. Let's try it. So let's set this up. How about if we do the height of the person over the shadow of the person, and then we could do the height of the wall over the shadow of the wall. Now before we cross multiply, it's totally appropriate to reduce when you can reduce, and then you can be multiplying smaller amounts. I love that. So I get 4 times h is equal to 30, and we divide. So it turns out that that man's height is 7.5 feet. Wow, must be an NBA player or something. And so there's a new twist on some shadow problems.